So very good morning to all of you. Today we are going to learn how to solve the system of ODE in method. We define the system of first order differential equation in the variable SYS underscore ODE. The command we start is actually to clear the previous memory and assign the first order differential equation ddt. ddt is actually you type using this button where the x you change it to t, f you change to I1t. How are you going to type the I underscore 1 in bracket t? For ODE in method you must put it whether it's function of t or x and so on. So how to type the I underscore 1? Let's see the expression when we have this one. This one, a underscore subscript an. Then a you change to I, n you change to 1. So di1 dt equal to negative 5 I1t plus 2 I2t plus 100. This is the first, and the first equation. Second equation is dt I2t equal to negative 2 I1t plus 40. So you have two first order differential equation. It become the system of ODE. And then the shortcut, you may just use the command dsolve. And when you put it, this is general solution. So for first order system of first order differential equation, we have two constants. So C1 is actually the A, C2 here is actually the B. Because you got two equations, you have two integral constants. So this is solution for the I1, this is a I2. This is using the built-in command dsolve. If plug in the initial condition where I call it as ICS, I1 is 0 equal to 0, I2 is 0 equal to 0, and you may get particular solution. Call it equal. Restart. I may not execute this one, so you give the errors. Or you can just execute the entire worksheets. So general solution, you have C1, C2. After you plug in the two initial conditions, the C1, C2 can be obtained. Then we will get this is actually the particular solution. So let's see how we type dsolve bracket SYS underscore ODE. This is the initial condition that we put it here. This is using the method equal to Laplace. Using Laplace. So you have curly bracket I1t comma I2t method equal to Laplace. This is using Laplace. This is using power series methods. Or you want to show step by step how we obtain the solution of system of first order differential equation. This is called the package linear algebra. A is coefficient of the first order system of first order differential equation, where here negative 5, 2. When the A is actually the matrix where we obtain from the coefficient of the homogeneous first order homogeneous system. Negative 5, 2, and then this is negative 2. We don't have I2, so it's negative 5, 2, negative 2, 0. This one. And then the characteristic polynomial is actually, okay, remember, okay, how we get this one? If we have a non-homogeneous system, to get the non-homogeneous system, first of all, we have to get the solution for the homogeneous system, where this one, the non-homogeneous parts equal to 0. We let this one equal to 0. Then we solve the homogeneous system first. Homogeneous system. Okay, this is manually. And we get, this is what we call the characteristic polynomial. Lambda squared plus 5, okay, lambda plus 4. Where, okay, to get the characteristic polynomial, we solve the determinant of your metric A in minus lambda at the diagonal. You get this characteristic polynomial. Okay, this is what here. Lambda squared plus 5, okay, lambda plus 4. Plus 4. And then, okay, after we get the characteristic polynomial, we solve for the eigenvalue. Okay, solving this one. Okay, we call the eigenvalue, okay, a function from the linear algebra package. We obtain -1 and -4. See manual. Okay, solving this quadratic equation, we get lambda 1 and -4, lambda 2 is -1. This here. Then with the linear algebra, this is another package. We solve, okay, the V1 is a eigenvector 1. And then V2 is an eigenvector 2. We define eigenvector V1 and V2. Okay, V1 as a x1, y1, V2 as a x2, y2. Here, using this statement here. And call back the A, the metric A. Then the equation 1 is actually, what's the equation 1 here? A minus eigenvalue A1 times identity matrix 2 times V1 is actually this step. Lambda, let's see. V1 -1. This one. Okay, after we solve, okay, the homogeneous system, when lambda 2 equal to -1 into the homogeneous system, A minus lambda I, A minus lambda I, V1 equal to 0. A minus lambda I, this is the identity matrix, V1 equal to 0, we get this homogeneous system in here. This is what we obtain here. -4 x1 plus 2y1, negative, okay, for the first equation. Okay, -4, 2. Where, okay, for V1, we already assign it as x1, okay, y1. So -4 x1 plus 2 y1, -2 x1 plus y1. Here. Using the statements, okay, A minus eigenvalue A1. We got two eigenvalues. So A bracket 1. Take the first eigenvalue. Take the first eigenvalue. So A minus lambda I. I is actually identity matrix 2. I mean it is a 2 by 2 times V1. It's actually this syntax. A minus lambda I multiply V1. So here, A minus the first eigenvalue. Okay, eigenvalue A minus lambda I times V1 equal to the matrix 2, 1, 0. We get this one. And then, okay, y1 is actually we solve, okay, from this eqn1 we solve y1. These two equations are equivalence. Equation 1 and the first and the bottom are equivalent. So we solve equation 1 here. Take the element number 1 respect to y1. So you get y1 equal to 2x1. Then by substituting x1 equal to 1, we get, okay, and then x1 equal to 1, calling back v1. So v1, remember we have the x1 is 1. So when x1 is 1, y1 will have 2. So this is what we have. Eigenvector 1, 2. 1, 2 here. Okay, equation 2 is actually when we substitute the second eigenvalue, a minus lambda, a minus the eigenvalue of the matrix A, which is negative 4. In here, substitute the second eigenvalue, a minus lambda I. Then v, 2 equal to 0, 0. This one. So a minus, this is substitute the second eigenvalue, which is negative 4, in the second eigenvalue. Okay. Multiply with identity matrix 2, means is your identity matrix is a 2 by 2. Multiply with v2 equal to the matrix 2, 1, 0 is actually 2 row, 1 column with the element 0, means the value is 0. Okay. And then you notice equation 1 and 2 here in EQ and 2 are equivalents. Means actually you have x2 equal to 2y2. So we solve x2, solve EQ and 2 number 1. We take this one respect to x2. So we got x2 equal to 2y2. Then we let y2 equal to 1. y2 equal to 1. So remember the second eigenvector, you have this is x2, y2 is 1, hence x2 is 2. So 2, 1. So 2, 1 here. So we already obtained the eigenvalue and its corresponding eigenvector v1 and v2. So the homogeneous solution will be the homogeneous solutions. A multiply v1 exponent lambda 1 t plus b v2 exponent lambda 2 t. So in maple, a times v1 multiply, a multiply your first eigenvector is v1 multiply exponent, this is a lambda 1, which is eigenval a, the first lambda 1 times t plus b multiply second eigenvector multiply exponent lambda 2t. So you get here, this is a homogeneous solution. And then the particular solution IP, since the homogeneous part, you have a non-homogeneous part, your mean the vector G, you have 140, because plus 100, second equation plus 40, means the vector G is 140. Hence, we assume the IP is also a constant vector. Because a non-homogeneous part is a constant vector, hence we assume the IP also a constant vector, that call it as U1 and U2, vector U1 and U2. So matrix bracket U1, U2. Then this is call back, show back the IP. IP bracket 1 is actually called U1, IP bracket 2 is actually you call U2. And the equation for the particular integral is actually what we are going to evaluate. EVAL is actually evaluate the system of ODE. I1t substitute with IP1, I2t substitute with IP2. then we'll substitute, okay, I1t here with the first, okay, the first row of the IP, I2 the second row of your IP. Then we, okay, because here this one I1 replaced by U1, this replaced by U2. Okay, if I1 is a constant, ddt I1 we got 0. If I2 is a constant, then dd2 I2 we got 0. That's why here is negative pi U1 plus 2 U2 plus 100. Okay. Negative pi U1 plus 2 U2 plus 100 equal to 0. So the seconds you have here dd2, okay, ddt I2t you get 0 equal to negative 2. This is U1 plus 40. Okay, and then we solve the n particular, okay, simultaneously. Okay, solve this, okay, n particular equation of particular integral simultaneously using the command solve. Solve this one for what? Okay, for IP1, IP2, where the IP1 is actually the U1, IP2 is actually the U2. So we obtain U1 is 20, U2 is 20. Okay, assign, then we'll plug in the value of U1, U2, okay, into the equation of particular integral. And when we call back IP, okay, in the value of U1, U2 will be plugged in, which is 20 and 0. And the I, okay, the IT is actually solution of homogeneous plus particular integral IP. So this 20 plus 0. Where, okay, this is a IH, this is a IH, this is a IP. Okay, and then notice that I here, this is equations, not functions. So to plug in t equal to 0, I use a eval I bracket 1, t equal to 0 equal to 0. Okay, and then eval I bracket 2, I bracket 1 in the first row. Okay, because what we have, the initial condition is actually what's our initial conditions? Okay, I1 0 equal to 0, I2 0 equal to 0. So this command is actually plug in I1 when t equal to 0 equal to 0. Okay, plug in the I2 when t equal to 0 equal to 0. So you got a plus 2b plus 20. This is true a plus b. And then we solve, okay, equation 20x here simultaneously for a and b. We obtain, okay, the value of a is 20 over third, b is negative 40 over 3. Then when we assign, okay, percent is actually the latest output. Then the a and b will be plugged in into the, okay, what's the I? I is the IH plus IP. I mean the value of a and b will be plugged in. So when you call back I, you get this is actually your particular integral. So here I repeat, we have solved the system of ODE using the shortcut method, which using the dsolve commands and manually using the linear algebra package, where you find, okay, you solve the homogeneous, okay, system solution using the finding the eigenvalue and eigenvector, eigenvector. And then it obtains, this is a homogeneous solution. Then it finds a particular integral. Choose a particular integral based on the form of your non-homogeneous part. We have actually 140, which is a constant vector. That's why the IP, we assume it as a constant vector too. And then the IP means the I1 is the U, I2 is the this is U1, this is U2. Okay. U1 substitute I1 is U1, substitute I2 is U2. Okay, when I1 is a constant, ddt I1 you get 0. When I2 is a U2, ddt the U2 you get 0. So that's what we put it here. Before the system ODE, plug in I1t equal to IP1, I2t equal to IP2. And then we solve these two equations simultaneously for U1 and U2. We get the IP. So to get the general solution of a homogeneous system will be solution of the homogeneous part. Plug in the add up with the particular integral. So you get this is general solution. To get particular solution, we need to plug in the initial condition. I1 0 equal to 0, I2 0 equal to 0. This statement. Then we solve for A and B. Then we get this is particular solution for system of ODE. With this, thank you for your attention.